Hello everyone, my name is Sathyam and I'm a third year student at Indian Institute of Information Technology, Sri City. And I welcome you all to the second section and the second lecture of System of Particles and Rotation Motion, where we deal with this chapter's PYQ. As I already mentioned in the previous class, that System of Particles and Rotation Motion is divided into two chapters, which is one is your center of mass and another is your rotational motion. So we will be dealing with the previous year question of both the chapters. A request to all of you is that please practice the JEE Mains questions and please even watch the previous sessions to understand and cope up with whatever the questions we are going to deal further. Okay, let's move to the question. So I will be beginning with the question number 20 over here, as you can see. Yes, I'll be moving with the question number 20 and let's start. All right. So kindly read the question, what they have given to us. A constant torque of force, a constant torque of, this is 1000 Newton meter, okay? Don't get confused. Turns a wheel of moment of inertia with kg, that is 200 kg meter square. All right. About an angle through its center. Its angular velocity after 3 seconds. So what will be its angular velocity after 3 seconds? Now, we know that the torque is given to us, right? The torque is given to us. Just have a look of this. Torque is equals to 1000 Newton. Fine, Newton meter. And they have given me inertia, moment of inertia. Now I know that I have a relation between torque and inertia. That is, tau is equals to I into alpha. Now how am I going to get the value of alpha? Using circular motion equations. Okay. So alpha is equals to W final, omega final minus omega naught divided by T. This is the formula. Okay. I have those values. This entire value is 1000 divided by 200. Okay. So this comes out to be 5 radians per second square. This is what you have to put it over here. What is, okay. So omega is equals to omega naught plus alpha into T, which is 0 plus 3 into 15. 3 into 5. And this is 15 radian per second. This is what the final omega they have asked, right? Final after 3 seconds. So that's why what I have done is, instead of T, we have put here 3, and initial alpha already have been calculated over here, right? We know the initial omega already, right? So this is the question which you have to do it. Okay. So the angular momentum of a body of a mass m. Okay. See what they have told us to calculate? Angular momentum. What is angular momentum, guys? It is denoted by capital L, right? Of a mass m and moment of inertia I, and the angular velocity is pi radians per second, is equals to what? So this is the simple formula, right? Simple formula. Now we know the derivation that, let's say that I have n masses and the distances through this masses from point OA axis is R1, R2, R3 and R4. So angular momentum of in every particle. We have to calculate angular momentum of every particle, right? That will be m1 v1 r1 plus m2 v2 r2 plus m3 v3 r3, correct? And from this, what I can take is that m1 is equal to, what is v1? V1 is nothing but, just a second. Yeah, v1 is nothing but omega, right? Just a second. Yeah, so what I was saying is that I have been given v1 over here, right? So what is v1? The value of v1 is omega into r1. Okay, this is into r1 plus m2 into omega is same everywhere, r2 into r2, and this goes on, right? So come to this. This is m1 r1 square, correct? Into omega plus m2 r2 square into omega, and this goes on. What is m1 r1 square? Just take omega as common. So this comes out to be the summation of from I equals to 1 to n mi r I square. This is what written. This is what is written, and this is omega. And we know that this quantity over here, which we can see, is nothing but moment of inertia I. So this is I into omega, whatever omega is left. So the angular momentum of a body is nothing but I into omega. All right. I hope it is clear. Cool. Let's go. Right. Let's go to the next question. Two particles which are initially, I'm sorry. Two particles which are initially at rest move towards each other under action of their internal attraction. All right. Two particles which are initially at rest move towards each other, okay, under the action of their initial attraction. Okay, so there was some attraction between the bodies, and due to that they are coming together. This is a bit of gravitation, I feel. Yes. So if their speeds are v and 2v at an instant, then the speed of the center of mass of the system will be, see, what they're saying is that I have two bodies, body 1, body 2, okay, which are initially at rest, moving towards each other. This is moving towards this. This is moving towards this. Okay. Let's say that this is moving with v speed and this is moving with 2v speed. So my center of mass is somewhere. Okay. Let's say this is the body and this is the body. Yeah. So my center of mass is somewhere on this line middle. Let's say my center of mass is here. But I know that if this body is moving here and this body is moving here, then my center of mass will accordingly shift. And this is what they're asking, that what will be the center of mass speed, because I'm considering that if this like we cannot consider any assumptions over here of masses, because it can be on purpose that this particle is moving slow, or it can be because of its weight also. So force acting on a rigid body, what is the force acting on a rigid body? It is mass into acceleration of center of mass, correct? And this is, what is the acceleration of center of mass? It is nothing but d2r by dt square. This everybody knows, correct? So force will be nothing but m into d by dt of velocity of center of mass, which is rate of change of velocity. What is the velocity? What is the velocity of center of mass? It is constant, that is 0. This becomes 0. That means that v of center of mass is nothing but constant. Okay. So when external forces act on its center of mass, will remain at the rest or move with constant velocity. This is what they're telling. 0. Okay. When no external force, because see, there's no external force. There is some internal attraction which is happening because of the bodies. Okay. So the center of mass will remain at rest or move with constant velocity. This is what they have given to us in this question. All right. Again, a very easy question. This question had come in 1998. A solid homogeneous sphere of mass m and radius r moving along the rough horizontal surface, partially rolling and partially sliding. During this kind of motion of the sphere, the angular momentum about the particle of the point of contact with the surface includes the angular momentum about the center. Due to the friction of linear momentum is conserved. Okay. So whatever happens, linear momentum will be conserved, right? This is one of the easy questions to apply. This is the answer. Okay. The angular momentum of the sphere about the point of contact with the plane is conserved. All right. I hope this is clear. Okay. Two disks of same moment of inertia rotating about their regular axis, passing through center and perpendicular to the plane of disk with angular velocity. Okay, there are two disks. They're passing through the center of a perpendicular plane. Okay. And the angular velocities of this disks are given to be as omega 1 and omega 2. All right. They are brought into contact force. Fine. They're brought into contact force to face coinciding the axis of rotation. The expression for the loss of energy during the process. What is the expression for loss of energy? Now we know that what is kinetic energy? Half I omega square, correct? Rotational kinetic energy. So the initial kinetic energy they have plus final kinetic energy they have given as twice. Okay. So omega is equals to omega 1 plus omega 2 divided by 2. There is the average. Okay. So kinetic energy initial is nothing but half I omega 1 square plus half I omega 2 square. What will be kinetic energy final? It will be half into 2 I omega square, that is equals to, I will take it out as it's common, omega 1 plus omega 2 divided by 2 whole square. So loss in kinetic energy is nothing but 1 by 4, okay, subtract KI and KEF, 1 by 4 I into omega 1 minus omega 2 whole square. All right. Okay. Right. So this is what we have. Yes, I guess we are through. Okay. So if you want further manipulation also, I can do it. Right. Let's say I want to do it. Okay. So what they have said is that kinetic energy initial is given as half I omega 1 square plus half I omega 2 square. And kinetic energy final is given to us as I into omega 1 plus omega 2 divided by 2 whole square. So what I have to do is I have to subtract, right? KE final minus KE initial, right? KE final minus KE initial, correct? Which comes out to be 1 by 2 I omega 1 square plus 1 by 2 I omega 2 square. This is one quantity minus I into omega 1 plus omega 2 divided by 2 whole square. All right. 1 by 2 I, I'm just taking it as common. Okay, fine. I'll just take 1 by 2 I as common. But a better way, what I can do is like this. I think this is better. This is what we are subtracting. Omega 1 plus omega 2 divided by 2 whole square, correct? This is what they are saying. All right. Now let's move further. What are we going to do over here? A square plus B square. What is A square plus B square? A plus B whole square minus 2AB I can write. Correct? That's what I can do over here. Let's try. Okay. So omega 1 plus omega 2 whole square minus 2 omega 1 omega 2 divided by 2. All right. Correct? Minus I into, this is omega 1 plus omega 2 whole square. Omega 1 plus omega 2 whole square divided by 4. Now I have to take LCM, correct? So if I take LCM, fine. Let's bring it on a blackboard. Okay. So this quantity, so this is nothing but I into, okay, just a second. Just a second, guys. Let us solve it further. Yeah, what does it say is, yeah, I into omega 1 plus omega 2 whole square minus 2 omega 1 omega 2 divided by 2, right? And this quantity over here is I into omega 1 plus omega 2 whole square divided by 4. Let us take LCM. All right. If you take LCM, this is going to be 4. Correct? Correct. It is 4. So this is going to be 2 into omega 1 plus omega 2 whole square minus 2 omega 1, that is 4, because 2 will get multiplied. 4 omega 1 omega 2. All right. ठीक है? And this is I. minus I into omega 1 plus omega 2 का whole square divided by 4. ठीक है. Now what I can do is I can subtract, that is 2 omega plus omega 2 whole square minus 4 omega 1 omega 2. Okay. So I'm subtracting, right? So it is subtracting, that is omega 1 plus omega 2 whole square. Okay. Divided by, well, let's say, okay. So this is divided by 4. All right. Now what can we do over here? So what can we do over here, guys? What we can do over here is that, see, this quantity, I'm getting 2 into omega 1. So I can subtract this quantity. So this will get cancelled by this 2, correct? So it is omega 1. Okay, let me be a bit clear. Okay. Yeah. So this is omega 1 plus omega 2 whole square. Fine. And over here I'm getting as 4 omega 1 omega 2 divided by 4. All right. So now what I'm going to do, I'm going to erase the top bottom. I hope you have understood until this point. We are just doing a random calculation. See, it is a very easy question. Your time is going to be invested in calculation itself. So I request you all to have a decent calculation practices. Okay. To avoid any such problems. Fine. All right. Just a second. Yeah. So I'm just erasing the top 2 parts. All right. I'm just erasing the top 2 parts. Notice we are over here, right? So what am I going to do? I'll open this. So what is a plus b whole square? A square plus b square plus 2ab, correct? And this is minus 4ab, and this is divided by 4. Okay, one more thing. You have moment of inertia outside. Okay, correct? I hope I'm not wrong over here. Okay, so let me erase even this part. Just a second. Okay. So I've got this. Now what I'm going to do, this is going to be cancelled. Okay, this quantity, this is plus 2 and minus 4. What is plus 2 and minus 4? That is minus 2. So I'm getting as omega 1 square plus omega 2 square minus 2 omega 1 omega 2, correct? And 4 is going to be over here itself. And moment of inertia I. Now what is this? A square plus b square minus 2ab. A square plus b square minus 2ab. That is a minus b whole square by 4. And this is I. And this means it is 1 by 4 I into omega 1 minus omega 2 whole square. See, I've got my solution. As you can see, 1 by 4, this is my solution. All right. This is what I've bought over here. You can just verify this once. Okay. It was nothing but a simple calculation thing. Okay. It was nothing but a simple calculation thing. Okay. Got it? I hope it is clear. This should be clear. Fine. Okay. We can move further now. Yes. All right. So this part is clear. See, it's just going to take your calculation time only over here, because initial kinetic energy and final kinetic energy calculation was very easy. All right. Okay. All right. Chalo. Let's move to the next point. Three identical spherical shells. Okay, 3 identical spherical shells, each of mass m and radius r, are placed on a, as shown, okay, as shown in the figure. Consider an image axis of, okay, x dash is the axis which is touching the two shells passing through the diameter of the third shell. Okay, moment of inertia of the system of consisting the spherical shells is about x dash axis is. This is the thing which we had discussed yesterday also. Okay, moving to the next question. The moment of inertia of a thin uniform rod of mass m and length L about an axis passing through its midpoint and perpendicular to its length I naught. Its moment of inertia about an axis passing through one of its end of the perpendicular lengths is what? Again, I is equal to I center of mass plus md square, that is I is equals to I naught plus m into L by 2. D square, what was D square? D square was middle of the length, right? So since it is middle, it is L by 2. All right. Chalo. A very famous question, 2011. A small mass attached to a a small mass attached to a string rotates on a frictionless table top as shown. So this is basically saying that I have a string and it is rotating with a small, okay, frictionless table, fine. Radius is r as it is shown in the diagram. If the tension of the string is increased by pulling the string, causing the radius of the circular motion to decrease by a factor of 2, then the kinetic energy of the mass will be. Okay, so what will be the kinetic energy of the mass? Very interesting question. So L will remain conserved, we know that. So I is equals to mr square, right? I is equals to mr square, correct? Fine. So what will be kinetic energy? Kinetic energy will be L square by 2mr square. All right. And in second case, kinetic energy will be L square by 2 into m r dash ka square. All right. As r dash is equals to r by 2. Fine. So kinetic energy final is equals to L square by 2m into r square by 4, which is 4L square divided by 2mr square. This means that the new kinetic energy is 4 times the original kinetic energy. Okay, kinetic energy the kinetic energy new is 4 times the older kinetic energy. This is what they have said in this part. So kinetic energy increased by a factor of 4 when no torque is applied and the angular momentum remains conserved, as we know this fact. So I1 omega 1 will be equal to I2 omega 2, and this is what written over here. Okay, fine. So E2 by E1, fine. E2 by E1 will be half I2 omega 2 square divided by half I1 omega 1 square, I2 by I1 into I1 by I2 ka whole square. Now this quantities will get cancelled and we'll get I2 by I2. Okay, we'll not get I2 by I2. This is a misprint over here. We'll get I1 by I2. Okay, we'll get I1 by I2. So if the moment of inertia is mr square, decreases the kinetic energy of the rotation and vice versa. So if moment of inertia is mr square, then it decreases the rate of rotation, and if the rate of rotation is decreased, then it means the moment of inertia is shifting to mr square. This is called vice versa thing. Okay. Now, next previous year question. This question had come in 2008, and the question says that the rotation of the radii of gyration. Okay, again a radii of gyration of a circular disc about the tangential axis in the plane of the disc and of a circular ring is same. So what they're trying to say is that disc and a circular ring is same. Okay, the same tangential axis about the ring is. Okay, so tangential axis about the ring, what they have said is that if moment of inertia is mr square, then the decrease in kinetic energy decreases, right? Same for ring and this thing. Okay, two bodies of mass 1 kg and 3 kg having position vectors I cap plus 2j cap plus k cap and minus 3 I cap minus 2j cap plus 3 k cap respectively, the center of mass of the system. Please recall the formula of center of mass, what I told you normally in coordinate system. Just take a moment and recall the formula. See, the formula of center of mass in coordinate system was m1x1 plus m2x2 plus so on upon m1 plus m2 plus so on, correct? Same goes for y, that is y center of mass is equals to m1 y1 plus m2 y2 plus so on divided by m1 plus m2 plus so on, and this is it. All right, simple. You just need to add vectors over there. Instead of adding the positions, you have to just add vectors over here. All right, this is what given to us. All right, so what you have to do over here is that m1 r1 vector plus m2 r2 vector divided by m1 plus m2, right? m1 r1 vector plus m2 r2 vector divided by m1 plus m2. Instead of keeping those normal coordinate points, I have just kept vectors. All right, fine. Okay, let's move to the next question. 4 identical thin rods, each of mass m and length l. So they have said that 4 identical rods are there, and we have same mass m and length l. Okay, that form a square. Moment of inertia of this frame about an axis through the center of the square. What is it? So we know that moment of inertia of a rod is 1 by 12 ml square, correct? So if these are the rods, entire system they have asked, right? This is one rod, C and D, fine. So moment of inertia is ml square by 12 plus ml square by 4. That is 4 ml square by 12. That is ml square by 3. Got it? Ml square by 3. So total moment of inertia is 4 into ml square by 3. All right. The moment of inertia of a uniform circular disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk. Moment of inertia of a uniform circular disk, okay? Uniform circular disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk is what? So this is what they have given to us. Please understand the solution. See. So we know that rotational energy is half I omega square, which is equals to half m k square into omega square, correct? This is linear kinetic energy, which is half m omega square r square. Now what is the fraction required? This is the fraction required. Then what I'm going to do, I'm just going to take a strip of an element at a distance r, and I'm just going to integrate that. All right. So as the density of iron is greater than density of aluminium, the whole aluminium is kept at the core and the iron is at outer rim of the disk. Simple. All right. Fine. So this question had come in 2006 as well as 2005. Fine. So the final solution over here, it is given. Okay. Half mr square. Fine. It is half mr square. All right. There is a flat uniform triangular plate. Fine. Flat uniform triangular plate ABC such that AB is equals to 4 centimeters, BC is equals to 3 centimeters, and angle ABC is 90 degree, as you can see in the diagram. Okay. The moment of inertia of the plane about AB, BC, and CA is I1, I2, and I3. Which of the following is true? Nothing. You just need to calculate normal moment of inertia. How do you calculate moment of inertia? I is equals to mr square. If you have multiple particles, it's sigma mr square. Just calculate upon distances of AB, BC, and CA, and you have angle of 90 degree. Don't forget 3 centimeters, 4 centimeters. Calculate it. So this is 16 and this is 9, so that's 25. So this will be 5 centimeters, right? AC will be 5 centimeters. So we can say that I2 is greater than I1 and I2 is greater than I3. This is what they have given to us over here. Okay. So I2 is greater than I1, and that's all. Option B. All right. Simple. Simple, right? This is 4 centimeters. This is 3 centimeters, they told. Hypotenuse theorem says that this will be 5 centimeters since it is 90 degree. Moment of inertia, sigma mr square. Correct? Sigma mr square. Calculate this. Calculate individually for this, individually for this, individually for this. Okay. So for ABE, your momentum inertia is I1, BCE is I2, and this is I3. You don't need to care about the angle. This angle 90 degree is only given only for this hypotenuse thing, to calculate the hypotenuse. So from this, I2 is greater than I1. All right. Great, guys. Let's go next. The moment of inertia of a disk of mass m and radius are about the axis which is tangential to the circumference of the disk. Again, it is tangential as it is saying, but it doesn't matter much because I will be shifted by mr square and id. So you just need to calculate id as it is given over here. So I is equals to id plus mr square. So 1 by 4 mr square plus mr square, that is 5 by 4 mr square. All right. 1 by 4 mr square plus mr square, that is 5 by 4 mr square. So the answer is 5 by 4 mr square. Fine. Let's move next. See guys, 1995 question and just this question which we discussed. Both are PYQs. Just what they have changed is that they hadn't given us this question. This is already calculated. We know that BC is greater than AB. I of 2 is greater than I of 1. See, exactly everything is same over here, as you can see. They had just mentioned I1, I2, and I3. And over here, they have just kept IAB, IBC, and ICA. All right. The rest of the angle is 3. Okay, this is 5. This is 3. This is 3. Again, values are just changed. The question is exactly the same. It's just that the values are this thing. Okay. All right. Fine. We'll move next. In a rectangle ABCD, BC equals to 2AB. Fine. In a rectangle ABCD, BC is equals to 2AB. The moment of inertia is minimum along through which direction? The moment of inertia is minimum out EG. Over here. And the reason for this is mentioned because mass distribution is minimum at the distance of EG. See, mass distribution is minimum over here, right? Mass is distributed over here, 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 and here, right? Mass distribution will be minimum at this point, the equator. Why mass distribution is important? Understand why mass distribution is important. Moment of inertia is sigma mr square, right? Mass is very important over here. Mass of a body is really very important over here. Okay. Radius is important, but they have just mentioned over here. So to calculate this parameter, we just need mass. Just check where the mass distribution is least. Okay. This question had come in 1993. Fine. Now, the moment of inertia of a uniform rod, uniform circular disc about a diameter is I. Its moment of inertia about an axis perpendicular to its plane and passing through a point on its rim. What will be rim? So the moment of inertia of uniform circular disc, let's say it is I. Now, according to the perpendicular axis, and you have perpendicular axis and parallel axis theorem, correct? So according to perpendicular axis theorem, half mr square, that is 2I. Okay. And then you apply your parallel axis theorem, since I is equals to 1 by 4 mr square, correct? And moment of inertia of the disk is given. This will be this, right? So this question was majority of perpendicular axis theorem and parallel axis theorem. All right. Fine. Let's move to the next question. The moment of inertia of a body about a given axis is 1.2 Just where initially the body is at rest. Okay, they're saying that initially the body is at rest. In order to produce a rotational kinetic energy of 1500 joule, an angular acceleration of 25 radian per second must be applied about that axis. So I is 1.2 kg meter square. I is 1.2 kg meter square. Correct. ER is 1500 joule. Alpha is this. Omega 1 is this. You need to calculate time. ER is given to you, which is kinetic energy, half I omega square. From this omega, you will calculate the value of ER. You just put it in the equation. You get ER as this. So W2 is equals to W1 plus alpha into T. This is circular motion equation. Okay, you're applying circular motion equation over here. So 50 is equal to 0 plus 25T. So 25 goes down and T is equals to 2. All right. Correct. I hope it's correct. Right. So 50 by 25, that is 2 seconds. Again, JEE 1990 question. I just want you to take a look at this and we'll be moving to the next question in a while. All right. A flying wheel of rotating about a fixed axis has a kinetic energy. Okay, it's a flying wheel of 360 joule when its angular speed is 30 radians per second. The moment of inertia about the wheel. Understand? It is a flying wheel rotating about a fixed axis. Okay. And they have given us kinetic energy. What is kinetic energy, guys? Understand what is kinetic energy? Kinetic energy is half I omega square. 360 is equals to angular speed half into I into 30. Correct? But you're saying I is 24. So there's a game of units. We have to do 30 into 30 and 360 over here. 30 into 30, right? Okay. It's a miscalculation over here. What I have to do is half into I into what is omega, man? 30. Omega square. So 30 into 30. And this is 360. Correct? So this gone. This gone. Fine. 3 threes are 9. So I'm just considering it as 9 into 10. So this is 2 ones are 2 fives are 9 fours are 36. Correct? This is 4 by 5. Right? This is I. What is 4 by 5? That is 0.8. 0.8 kg meter square. It was a very easy question. You just need to know the formula that ER is equals to half I omega square. All right. This is what you have to know. Fine. Now moving to the next question. As you can see, this is the solution of this question. Okay, we have option C as our answer. A disc of radius 2 meter and mass 10 kg rolls on a horizontal floor. Its center of mass has a speed of 20 centimeter per second square. How much work done is needed to stop it? So kinetic energy. See, work done to stop the disc is change in kinetic energy of the disc. Final kinetic energy is 0. Initial kinetic energy is half mv square. As it is linear plus half I omega square as it is even rotating. So half mv square plus half mr square by 2 into v by r whole square. This is half mv square plus 1 by 4 mv square, that is 3 by 4 mv square. So 3 by 4, what is m? 100. V square is 20 into 10 ki power minus 2, as it is in centimeters. 3 joule. So change in kinetic energy was 3 joules. Okay. Now I'll tell you the mistake. The mistake which can happen in this question is of units, which is this. Radius is in meters. This is in kgs, but this is in centimeters. So what you have to do, you have to bring this in centimeters. All right. And there you have your answer. This is what you had to multiply, 10 ki power minus 2. Rest all the question is same. And you should even know that the initial kinetic energy will be translation plus rotational kinetic energy. So the change in kinetic energy which is given to us is 3 joules. All right. Let's come to question number 40. A solid cylinder of mass 2 kgs and radius 50 centimeters rolls up an inclined plane of angle of inclination 30 degrees. The center of mass of the cylinder has a speed of 4 meters per second. The distance traveled by the cylinder on the inclined surface will be 2019 NEET question. Okay, this has come in NEET Odisha. Okay. So kinetic energy at the bottom, half mv square plus half I omega square, that is 3 by 4 m naught mv naught square. For the solid cylinder, moment of inertia is half mv square. V is r omega. So using work energy theorem, 3 by 4 mv naught square, that is equals to mgh, is equals to mgd sine theta. Do you know what is this? They are saying that kinetic energy, change in kinetic energy is equals to gain in potential energy. This is what the equation is written over here. Using this, you have got d, and using d, you can put in this question. Through that, you will get d is equals to 2.4 meters. Okay, this was a very good question. As a NEET level, this is a very good question. Okay, 2016 JEE Mains. A disc and a sphere of same radius but different masses roll off on two inclined planes of the same altitude and length. Which of the following objects are going to get the bottom first? So using time of descent is directly proportional to k square by r square, correct? The order of value of k square over here is 0.5. And here it is 0.4, right? Sphere is less than disk. As you can see, the time of descent, which means that sphere will reach first. So sphere is going to obviously reach first. Okay. Let's move to the next question. A solid sphere of radius r is placed on a smooth horizontal surface. A horizontal force F is applied at height h from the lowest point for the maximum acceleration of the center of mass. 2002. As friction is absent at the point, okay, because they haven't even mentioned anything else. So friction they have not mentioned. See, if they have not mentioned, we'll not even consider friction. Okay. So normal acceleration formula, which is force upon mass, it comes from F is equals to, okay, it comes from F is equals to ma, right? From F is equals to ma. Now force is equals to mass by mass into acceleration. So acceleration is equals to force by mass. We don't have anything related to height, so it is independent of the height. It doesn't matter whatever it is, acceleration will remain the same. See, if friction would be there, then the story would have been different. Okay. JEE 2002. A solid cylinder of mass m and radius r rolls down an inclined plane of height h without slipping. The speed of its center of mass. Again, gaining kinetic energy is equals to loss in potential energy. So just calculate kinetic energy, which is, this is rotational kinetic energy and this is translation kinetic energy. Okay. Kinetic energy calculate kar liya, so you have got 3 by 4 mv square, which is mv square, which is loss in kinetic energy is equals to gain in potential energy, which is mgh. So you have to calculate the value of v, which is under root of 4 by 3 g into h. All right, this is the thing. A solid sphere, disk, and solid cylinder, all of the same mass and made of the same material, are allowed to roll down from rest. Okay, from rest. So V initial is 0 on the inclined plane. Then you can say that the solid sphere, they have calculated. Again, this is the time of descent question. Okay, time of descent question. So this is what they have given for time of descent of a sphere. Similarly, of a disk and a cylinder. Okay. So as k square by r square of sphere is the smallest, it takes minimum time to reach the bottom. Okay. Where bodies of different shapes are allowed to roll down the inclined plane, the velocity of the bottom of the incline acceleration and the time taken in reaching the bottom of the sphere is k square by r square. That is time of descent, whatever we know that. Okay. If the body has less moment of inertia, then k square by r square will be less. So that is the reason we had calculated moment of inertia, because moment of inertia is directly proportional to k square by r square. Okay, understand? Then it takes less time to reaching the bottom. So moment of inertia, यहाँ पर we saw that solid sphere का सबसे कम था, the least, and the disk it was 1/2, and this is 2/5, so this is least. So the sphere takes more time. I mean, the sphere, solid sphere takes less time to come to the inclined surface. Okay, so sphere, this takes less time rather than a cylinder or a normal disk. Okay. Okay, so this is the last question which we will be dealing. Fine. The center of mass of a system of particles does not depend on what of the quantities. The center of mass of the system depends upon position, mass. Okay, position and mass. Also, it depends on relative distance between the particles. Fine. So it depends on mass. It depends on position of the particles. It depends on the relative distance of the particle. It does not depend on the force. Okay, so this is our correct option. This is our correct option. Why? Because see, what is center of mass? XCM is equals to M1 x1 plus M2 x2. Let's say that I'm just calculating for x coordinate. Okay, let's say. Okay, fine, I'm not. I'll calculate for both the coordinates. That is M1 plus M2 plus M3 plus so on. And what is YCM? YCM is equals to M1 Y1 plus M2 Y2 plus M3 Y3 and so on, divided by M1 plus M2 plus M3, and this goes on. This is for a system of particles where this is my particle M1. Okay, this is my particle M2. Okay, particle M1, particle M2, particle M1, particle M2, and okay, yeah, and this is separated by a distance. Here is my center of mass from x1, and this is x2. Center of mass is over here. So the coordinates is xcm and ycm. Okay, this is my center of mass, and this is the formula which is given over here, right? So mass of the particles is counted, yes. Position of the particle is obviously counted, right? Where the position are, right? And the relative position, that is x1 and x2, obviously, correct? These two quantities are. Is there any force acting upon this? Why? Because center of mass, see, center of mass is nothing but a coordinate. Okay, so force acting on this particle will not be telling anything about it. All right, so this is what I would like to tell over here. Fine. Yeah, so center of mass depends upon position, mass, and okay, position and mass, as well as relative. See, what is the relative distance of the particle mean? See, relative distance is like if you look at a 3D point of view. Okay, these are circles. So these center of masses are at a global coordinate system. Okay, let's say I want to calculate center of mass of this particle and this particle. So this is another position, and this is another position, right? So these are normal distances, right? It depends on the distance. It depends on this red. How far there, it actually depends on that. Okay, and what is the relative distance? That how far is this particle from this particle, and how far is this particle from this particle. So depending upon this particles, the particle B, let's say, and this is particle A and this is particle S, let's say. So depending upon particle B and particle A, my center of mass will be shifting somewhere, right? If this mass is getting bigger, my center of mass will be shifting over that side. If this is getting bigger, this will shift over here. If this is getting bigger, this is going to shift a bit of this side. Understand this thing? Okay, so this is relative position. Mass already I've told, position already I've told, relative position, relative distance between matters, this distance and this distance, or what is the distance between this particle sometimes. Okay, all right, so this was the concluding question, guys, and the final solution of this question. Now, a few points I would like to mention. What we have learned from this chapter is that few points you have to understand that center of mass calculation is very important. Okay, rotational motion. In rotational motion, just go for moment of inertia. Okay, and if you get time, then linear momentum, angular momentum. Fine. You have torque, but actually torque calculation comes over here itself. But okay, so moment of inertia and CGM. Okay, just understand that this chapter will give you a weightage of 3 to 5 questions. And yes, there are some questions where nobody does it. Okay, so you have to make sure that you are actually perfect doing the questions. Fine. This is one request for you all, that at least learn how to do center of mass calculation and moment of inertia calculation. Okay, because out of this 45 questions what we have dealt in these 2 classes, moment of inertia calculation is around 20% of the weightage, though it is not significant over here, but in exam, each and every mark, each and every question will be important for you. So center of mass, moment of inertia, these 2 things are to be calculated. These 2 things is what you have to do. All right, fine. This was one thing. And the next thing what I want to tell is that, work energy theorem. Work energy theorem is very important for both the chapters, because see, work energy theorem, center of mass, COM, and rotational motion goes hand in hand, and this is what the real mechanics is. Okay, this is what the real mechanics is. Actually, the real mechanics start from here, because rotational motion is a combination of all the chapters what you have studied in the past. All right, in mechanics. Fine. So it is a humble request that you people go for this, because see, we had even dealt the questions regarding kinetic energy and potential energy also. So that is also where the thing is going to be applied, right? For a safer side, go for a work energy theorem, go for center of mass, go for moment of inertia. When this is done, then you can go for linear momentum conservation, angular momentum conservation, you have torque, then you have many other stuffs, right? Slipping and rolling motion and all those stuffs, right? Correct? So prepare well, and for the PYQs, I would suggest that solve the PYQs from 2019 of NTA. That will be more relevant. Okay, if you have any doubts, you can put down your doubts. We'll be there to clear for you. I hope you have understood this classes, what I have taught you of this chapter. We'll be meeting in the next sessions. Okay, so thank you very much.